In conventional wastewater treatment systems, the aerobic removal of organic matter is carried out by ordinary heterotrophic organisms, OHOs. Under aerobic conditions, OHOs consume the organic matter and use it as an electron donor and also as the carbon source to produce new cells. Usually, organic matter is measured as chemical oxygen demand, COD. Meanwhile, oxygen is used as the electron acceptor to generate the required energy for biomass synthesis through the catabolic reactions. OHOs also need nutrients for cell growth, like nitrogen, phosphorus, among other macro and micronutrients. Thus, through the anabolic process, more cells are produced. Other compounds, like carbon dioxide, are also generated as final products of the biological reactions. Usually, the main kinetic parameter of interest is the maximum chemical oxygen demand uptake rate. This parameter indicates the maximum speed at which the biomass present in the activated sludge can remove the organic matter present in the bulk liquid under the applied conditions. This kinetic parameter can be determined by linear regression, taking into consideration the first chemical oxygen demand concentrations measured in the bulk liquid at the beginning of the test. Preferably, the linear regression trend line should be fitted to at least 4 to 5 data points, with a coefficient of determination, R2, not lower than 0.9 and ideally as close as possible to 1. The purpose of this video lecture is to show the basic principles for executing a batch activity test for determining the aerobic removal of organic matter. For this purpose, a batch reactor is used. In particular, it is equipped with an air supply line to create the required aerobic conditions through the sparging of air. The reactor should also have ports to collect the required water samples to assess the reactions, and to add the source of organic matter, usually wastewater or organic solutions. In this example, acetate is added as a source of organic matter and it is measured in terms of chemical oxygen demand. To carry out the test, it is highly recommended to prepare a working sheet. The working sheet should summarise all the steps that need to be followed before, during and after the execution of the test. The working sheet should also include the sampling times, as well as relevant information regarding the analytical parameters that need to be determined with each sample.
This test is performed in one aerobic reactor. Prior to the execution of the test, verify that your setup is ready and that your pH and dissolved oxygen meters have been calibrated. Place all your working material next to your setup to ease the conduction of the test. After the sludge has been collected and washed, if applicable, it should be carefully poured into reactor 1. Before pouring the mixed liquor into the reactor, mix carefully the sludge to get a homogeneous sample. This will avoid that the biomass settles and remains at the bottom of the bucket. Repeat, if necessary, until pouring the required volume of sludge into the reactor. Once the sludge has been poured, close the reactor and start up the stirrer. Verify that the speed is adequate to keep the sludge sample well mixed. Otherwise, increase the speed until the mixed liquor looks homogeneous. Confirm the steps to be followed and their sequence in the working sheet. Verify that the operating and environmental conditions are stable and within the expected ranges. If desired, alloenthuria can be added. ATU will inhibit nitrification when the sludge is aerated. Usually, 20 milligrams per litre of ATU are sufficient to inhibit nitrification. After the addition of ATU, close the reactor. Start the aeration and aerate the sludge sample for 30 minutes. To aerate the sample will help to remove any residual biodegradable organics. After aerating the sludge sample for 30 minutes, continue with the next steps of the test. Confirm there is neither sludge stratification nor dead volumes. Also, verify that the operating and environmental conditions are stable. If the conditions are stable, the preliminary samples can be collected. The sludge samples need to be homogeneous and representative. Thus, the external aeration can be temporarily turned off to avoid the excessive presence of air bubbles in the samples to be collected. The preliminary samples will be used to determine the initial concentrations of the parameters of interest. Tightly connect the syringe, avoiding the intrusion of oxygen, and push and pull at least 5 times until a homogeneous and representative sample volume is collected. Close the sampling port with a clip to avoid spillages. To preserve the samples, place the samples in ice. If possible, the samples have to be collected in triplicate. For the determination of the soluble compounds of interest, filter the samples through 0.45 pore size filters. For the determination of the soluble compounds of interest, Filter the samples through 0.45 micrometer pore size filters. Do not apply excessive pressure, thus avoiding that the filters break. Consider the use of at least 2 or 3 filters per sample, because they will likely clog and may break if excessive pressure is applied. This will also contaminate the filtered sample. If the external aeration was temporarily turned off, do not forget to switch it on after the preliminary samples are collected. Continue with the test after the acclimatization of the biomass in the reactor to the expected operating and environmental conditions and after the collection of the preliminary samples. Prepare the addition of the carbon source of interest. Collect the required volume of the carbon source to be added in a syringe. Avoid any presence of air bubbles. Add the carbon source solution firmly and fast into the water phase. Simultaneously start the stopwatch. This will be the beginning of the aerobic batch activity test. Close the reactor. After the addition of the carbon source solution, confirm the times of the sampling program. Arrange the required sampling material and continue with the collection of the samples as planned.
it is important to filter the samples at the corresponding sampling time. Thus, start with the collection of the samples around 20 seconds before the time indicated in the working sheet. To filter the samples at the time indicated in the sampling program will help in the correct determination of the kinetics of the processes. Thereafter, continue with the sampling program for soluble and particulate compounds as planned and described in the working sheet. Throughout the test, confirm that the required operating and environmental conditions have been stable and within the allowable operating ranges. In the end of the test, the external aeration can be switched off. This will help to minimise the presence of air bubbles in the samples that will be collected for the determination of the concentrations of particulate compounds and suspended solids. Thereby, collect the last required samples following previous recommendations for the determination of particulate and soluble compounds. confirm that all the required samples have been collected. If possible, carry out immediately the analytical determination of the parameters of interest. Otherwise, follow the required procedures for the preservation of the samples until they are analysed.
At the end of the test, confirm that all the required samples have been collected. Verify the stability of the parameters of interest and stop the operation of the reactor. If possible, carry out the analytical determination of the parameters of interest immediately. Otherwise, follow the required procedures for the preservation of the samples until they are analysed. After the execution of the test and the determination of the parameters of interest in all the samples, all the data can be compiled and displayed in the working sheet. The results of the chemical oxygen demand measurements determined by the batch activity test can be plotted as a function of their time of collection. Thereafter, the maximum volumetric chemical oxygen demand removal rate can be determined by linear regression. This is carried out by fitting the first chemical oxygen demand measurements and through the determination of the trend line that provides the highest determination coefficient, R squared. Thus, the maximum volumetric chemical oxygen demand removal rate corresponds to the slope of the equation that describes the trend line. In this example, the maximum volumetric chemical oxygen demand removal rate is 378.86 milligrams of COD per litre per hour. Considering that the average mixed liquor volatile suspended solid concentration is 1,769.5 milligrams per litre, the maximum biomass-specific aerobic COD removal rate is 0.21 milligrams of COD per milligram of volatile suspended solid per hour, or 5.14 grams of COD per gram of volatile suspended solid per day. This rate is comparable with the typical rate of 5 grams of COD per gram of volatile suspended solids per day reported in the literature and as shown in Table 2.5.1 of the textbook.